Hey guys, hope all is well at home. This is going to be the first tutorial video that I post for new material. So we are starting chapter 11, which is on space figures, aka the land of 3D. We're moving out of just two-dimensional shapes, and we're going to get things to be a little bit more exciting by looking at three-dimensional solids. So today we're going to look at what are called polyhedra, and we're going to talk about what are called cross-sections of shapes. And I'll post one of these tutorial videos for you for every new section that we do from here on out during e-learning. I wore my 3D shirt today, so what you got on there is a rectangular prism. And if we were to actually measure the side lanes, maybe it's a cube. Maybe that'd be a good activity for me to do later. So that just goes to show you I wear these shirts at home, not just at school. What I'm going to do is share my smartboard doc with you. And you should have this at home with you as well. And if I need to talk and have you see me during the actual video, I will present myself, but right now I'm going to hide my camera so that you're focused more on the notes, but my voice will still be here. All right, so I'm going to present my screen. Okay. So you should see my 11.1 thing now. Let's see. Yeah, there we go. Sorry, let's just make sure the tech is working there. Okay. Flip this around. So as I said, we're going to talk about what are called polyhedra, and we're going to talk about cross sections of these space figures. And space figure just means 3D figure. What you have here is what's called a polyhedron. This one's pretty cool looking. It's made up of a whole bunch of different polygons, and that's exactly what a polyhedron is. It's a 3D figure whose surfaces are all polygons. Could be triangles, could be quadrilaterals, hexagons, dodecagons. Could be a whole bunch of different ones. You fold them all up and make this enclosed figure. That's what we call a polyhedron. There's different vocabulary that we use for polyhedron. So kind of starting with the actual polygons themselves, I'm going to do these in red. I'll highlight two of them for you. This polygon, and there's 6 of them in this picture. But these polygons that make up the figure are what we call faces. So faces are just the polygons making up the figure. Anytime 2 of those polygons intersect, you're going to get one of these segments. So I'm just going to draw two or three of them in blue for you. There's a whole bunch of them in the picture. But the intersection of those faces, these segments that you see in the picture, are what we call edges. So the edges are where the faces intersect. And then if we zoom in even further, what about where those edges intersect? Those segments, those edges are intersecting at the corners. So all of these green dots that you see me posting are what we call vertices, which is a word that we've seen before. Okay. So faces are the polygons, edges are the segments, and the vertices are where the segments meet up, just the dots in the corners. Okay. So here's another example of a polyhedron. This specific one is called a pyramid. We'll talk about those more in the middle of the chapter. And you'll notice what I did from here to here is I unfolded that pyramid so that it's now just a two-dimensional object. And what that really allows you to see is all of the faces individually. I can see it's made up of 1, 2, 3, 4 triangles, and it's made up of one, we would have to measure to see if it's a square, so we'll call it a quadrilateral for now. But this is what we call a net diagram. It's a two-dimensional unfolding of a 3D figure. So this is what we call a net diagram. It's a 2D unfolding of a 3D figure. And we'll be drawing some of those and analyzing some of those in a little bit. Okay, first thing, let's identify some vertices, some edges, and some faces for this pyramid that I have here. And it's really just a counting game. First question wants to know how many vertices are there in this polyhedron that I have on the left-hand side. That's just all the dots where the edges meet up. So I'm just going to count in red. 1, 2, 3, 4. I count 5 dots. So there are 5 vertices to that shape. How many edges are there? This is where all of the vertices connect, all the segments in the picture. Get 1, 2, 3, 4. Get that 1 in the back. And then you get 4 on the bottom for that square. 1, 2, 3, 4. So we had 4 going up to the top and 4 on the bottom. 4 plus 4 is the magic number 8. How many faces are there? Well, there's 4 triangles surrounding the shape. There's 2 front and back, and there's 2 left and right. 1, 2, 3, 4 triangles, and then I have a square on the bottom. So that gives me 5 faces. That's really just a counting game. There is a cool relationship between the number of vertices, the number of edges, and the number of faces that was discovered by a mathematician by the name of Leonard. And take a guess if you can figure out how to pronounce this. Many people think it's Euler. It's actually not correct. It's Euler. So if you were to pronounce it phonetically, think of like the oil you put in your car. Leonard Euler was a mathematician who discovered this relationship for the number of vertices, the number of edges, and the number of faces of a polyhedron. The relationship that he discovered was that if you actually know 2 of the pieces of information, you can solve for the third. If you have a 3D object, the number of faces plus the number of vertices is equal to the number of edges plus 2. And that's the real important part at the end. Even though it's a 3D object, we're only adding on 2. So that number right there is 1 less than the number of dimensions of the entire shape. Okay? So the number of faces plus the number of vertices of the 3D figure is equal to the number of edges it has, but you have to make sure you add 2 onto that. So let's kind of confirm that for the one we had up here. Here was my pyramid. Does it work with the numbers that we found? Let's see. Does the number of faces plus the vertices equal the edges plus 2? Well, there's 5 faces. We counted 5 vertices. Number of edges we counted was 8. So does 5 plus 5, 10, equal 8 plus 2? 10 does equal 10. Check. So that's what we call verifying that the formula works. We make sure the left side equals the right side. Now, down here, what we're going to do is we're actually just going to count up 2 of those pieces of information, and we're going to use Euler's formula to solve for the third. So we're going to count up the faces, and we're going to count up the edges. So the faces, I'll do in green. Okay. In this one, this is what we call a prism. I've got 2 hexagons, one on the top and one on the bottom. So if I'm going to keep track of my faces, I've got 2 hexagons. And then you'll notice I have 3 rectangles in the front and 3 rectangles in the back that are connecting those 2 hexagons together. So I also have 6 rectangles. So if you add those up, that gives me 8 faces. Edges I'll do in blue. You got 6 on the top for this hexagon. You got 6 on the bottom for this hexagon. So keeping track so far, 6 plus 6. And then every rectangle has 2. So if I count these up, 1, 2, 3, 4, 5, and 6. Get another 6 edges from the rectangles connecting top to bottom. So I get 18 edges. And now what I want to do is I just want to use Euler's formula to compute the number of vertices without having to count up all these red dots. That would just be a pain. So F plus V equals E plus 2. I'm going to plug in what I know. There's 8 faces. We don't know how many vertices we have. So I'm going to highlight. That's the variable we're trying to solve for. We counted 18 edges, and then we make sure we add on 2. So 8 plus V equals 20. Then I solve it like an algebra equation. I'm going to subtract 8 from both sides. And I would see that there are 12 vertices to that polyhedron. And you can count them. If you wanted to confirm that for yourself, there would be 12 dots in the picture you could count. So that's how you use Euler's formula if the shape is 3-dimensional. What if you just want to look at the net diagram and use the same exact logic? Find the number of faces, find the number of vertices, number of edges. Well, if you're looking at a 2-dimensional net, okay, the formula is almost the same, except you'll notice now instead of adding E plus 2, we add E plus 1. It still has that same pattern. Because my shape is now 2-dimensional, I'm going to drop that value by 1 when I use the formula. Okay. So what's the summary? If you're looking at a net diagram, you need to use E plus 1. If you're looking at the actual 3-dimensional object, you need to use E plus 2. Okay. So make sure you're being careful with that. So for example, there's the same prism we just looked at. Here's the net diagram unfolded. You can see the 2 hexagons and you can see the 6 rectangles if you were to unfold that shape. So I want to verify that this works. Verify means I'm plugging in for everything. So I'm going to confirm that f plus v is equal to e plus, I'm going to use 1 because I'm looking at the net diagram. That's why I'm not using plus 2. Okay. How many faces do I have? Well, I got 2 hexagons and I got 6 rectangles, so I got 6 faces. Plus vertices, we're just going to have to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Number of edges I'll do in blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, we already counted that one. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Looks like I missed something. Oh, apparently I can't count. There are 6 rectangles plus 2 hexagons. That's 8 faces, not 6. Let's erase that. My bad. 10. Right, so 2 hexagons, 6 rectangles. That should be an 8. Plus 1, so 22 plus 8 is 30, and 29 plus 1, last time I checked, is also 30. So that's what we mean by verify. Plug in F, V, and E and show the left side is equal to the right side. Next one we have is a trapezoidal prism. We want to verify that our formula works for 3 dimensions. Okay, so trapezoidal prism, reason it's called trapezoidal, you got a trapezoid in the front and the back. For 3 dimensions, remember it should be F plus V equals E plus. Take a second. What do you think? 1 or 2? Give yourself 2 or 3 seconds. Put down your prediction. Drum roll. It should be E plus 2 because we're looking at a 3D object. So counting, I have 2 trapezoids. I have 4 rectangles, 1 on the top, 1 on the bottom, 1 on the left, 1 on the right. So I have, I'm going to get my counting correct this time, 6 faces. Vertices, 1, 2, 3, 4, 5, 6, 7. Ah, got that little guy at the top right corner. There's 8. Edges we'll do in green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I missed one. Where'd I miss one? There it is. 12. 12 edges plus 2. And 14 does, in fact, equal 14. What I'm going to do now is draw the figure in 2 dimensions, which means I am making a net diagram. So if I draw this in 2 dimensions, the first thing I'm going to do is going to create a rectangle to start with. I'm going to draw the rectangle on the bottom. And connected to that rectangle are 2 trapezoids. So if I was to unfold this, I could put one of those trapezoids there, and I could put the other trapezoid there, connected to that rectangle on the bottom. So that kind of gets me started. That's me just unfolding 3 of those faces. But there's also 1, 2, 3, 4 rectangles I still haven't, or let's see, no, 3 rectangles I still haven't included. I got this one on the left-hand side. I'm going to connect that one on the right. And then I've got this one, but I've also got the one on the top. So those 2 are going to have to go next to each other. So 1 rectangle, and then I get another rectangle. So that would be my 2-dimensional unfolding of that 3D prism. Let's verify that Euler works for 2 dimensions. Erase these dots. Okay. So this time I'm going to do F plus V equals E plus 1. Well, I got 4 rectangles, 2 trapezoids. I got 6 faces. You can count up the vertices in this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 vertices. count up the edges. Do that in pink. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I get 20 equals 20. And again, that's what verify means. Verify means you have to plug in for all three variables. If they wanted you to solve, you would be only plugging in for 2. So that kind of wraps up Euler's formula. The last thing we're going to talk about is what is called a cross-section. And the best way to think of a cross-section is it's really just a two-dimensional slice of a 3D figure. So a cross-section is just a 2D slice through a three-dimensional object. And obviously, depending on how you slice through the object, you could get a very different shape. So a really good way of thinking about this is like if you have a knife and you're going to slice through a specific object, like maybe you're cutting bread. Depending on how you slice the bread, you're going to get a different shape. Okay? So I'll give you an example. I'm going to switch back over to my mode so you can see me. Okay. Okay. Stop presenting. You should now see me. Okay. Here is a three-dimensional Post-it note stack. Okay, clearly a 3D object. It's got length, width, and it's got height. Depending on where I were to slice through this Post-it note stack, pretend my hand was a knife right now. If I was going to slice through horizontally right now and slice through this stack, what would happen is if I slice through, the cross-section is going to be what you see when you take out one of the sheets. So my cross-section, when I cut through horizontally, if I was to slice this way, would just be one of these two-dimensional rectangles. So think of it this way. It's when you slice, it's the shape that you see, the two-dimensional object. Okay? So it's just a slice out of your 3D stack. If I was going to slice it vertically, this would require some very, very heavy-duty scissors, but pretend I was to cut this way, what you would end up seeing is this little shape right here. So I'll try and outline it in green so you can see it. It's hard to write on this uneven surface, but you get the idea. If you were to pretend like that little surrounding area is what I had, that would be my cross section if I was to be slicing through this Post-it note stack vertically. That would be the vertical cross section. And there's many other ways you could slice through it, but horizontally and vertically are two of the most popular choices that you can get. Okay? And I will post a little funny video later that I made called cross-sectional cooking. And you can see me do some cross sections with a stick of butter. So that will be up shortly. All right, I'm going to go back to presenting. Hide myself, but you should still hear my voice. Okay, so back to our notes. So a cross section, as I said, it's a 2D slice. So let's kind of take a look. What shape does each cross section create? And it's important that you look at which way you're slicing it. Okay. In the first one, think of this as almost like the note card stack that I just had. Is the cross section horizontal or vertical? Well, in this one, I'm going up and down. If that was my knife, that little green sheet that you see, it's slicing it from top to bottom. So if you were to remove those two stacks from the Post-it note, the shape that you're going to get is just this little square. That's what you would see on the inside, would be that little square, no matter where you slice. In the second one, I'm slicing horizontally. If you notice, it's moving now from left to right. Okay? So this would be me slicing from left to right. Well, if I was to slice from left to right, what I'm going to see no matter where I slice in the middle, if I was to look down, okay, I would see a little triangle, okay, no matter where I slice. It could be in the middle, it could be near the bottom, but it's always going to slice into a triangle. Let's look at the funnel. If I was to do a horizontal cross section, so pretend that I was cutting this way, pretend that you were on top right here and you're looking down into the shape. What you're going to see if you're slicing horizontally from left to right is you're going to see a circle. Now what's going to happen is, depending on where you're at up and down on the shape, those circles are either going to be bigger or smaller. If you're near the top of the funnel, you're going to get a big cross section, big circle. If you're near the bottom of the funnel, you're going to get smaller circles. So the size of the cross section can actually change with this funnel. Okay? But no matter where I slice, if I was to look down into the shape, that horizontal cross section is going to make a circle. Let's do it vertically. Oh, no, eraser. So if I was to do a vertical cross section, now I'm taking my, again, think of it as like a knife. If you were going to take your knife and slice up and down, or if you're like a ninja, you're taking your sword and slicing it up and down, now you're trying to slice this way. Well, if you're slicing up and down, what you're going to get is this little outline right here. So the cross section that you get almost looks like the letter Y. It's like a trapezoid connected to a rectangle without putting this part. Okay. Why don't you take a minute and try this one? You can pause me, and once you're done, I'll have an answer put up you can use to check. Okay, so hopefully you had a chance to draw the cross section. It's important that you make note that it is a vertical cross section, which means we're slicing up and down. Okay, we're not slicing through the shape left to right, we're slicing it from top to bottom. It's a cube, and what's nice about a cube is that means you have all square faces. So if I'm going to slice up and down, every single time I slice, what I'm going to see, no matter where I slice, is going to be a little square. Whether I slice it here, whether I slice it here, think of it as my Post-it note stack. I could even slice it right at the edges. Every single one of these little sheets that I get is a square. So that would be what my vertical cross section creates. So that should do it for the notes. All right, that should do it for this video. Math Excel will be posted, and I will have another one of these up for 11.2. Take care.